Hi all, Dr. Clark here again, and we're going to continue talking about population dynamics. Okay, when we stopped last time, I had just introduced the two types of growth curves or population growth curves. The exponential growth curve, which is going to be J-shaped, and the logistic growth curve, which is going to be S-shaped or sigmoidal. Okay. Well, we're going to dive into a little bit more uh, information on what you can do with the different graphs, what the different regions of the graphs tell you about a population. And then we're going to talk about the Isles Royale again, just so I can reiterate what population dynamics and predator-prey models can do for management, for whether that be fisheries management or wildlife management. Okay, so we left off, we were talking about this example quite a bit, the lynx hare example. It's a classic example of a predator-prey cycle. Prey increases, predators follow with an increase, that decreases the prey, then that decreases the predator, etc., etc., etc. Okay? And like I said, we've known about these cycles for a very, very long time, especially the lynx hare cycle. But like I said, there's other ones, and there's elk and wolf cycles, there's moose and wolf cycles, there's goshawks and grouse. There's just a lot of cycles. Some fit a pattern that is very predictable. You have a big year of rabbits, 2 years from there, you're going to have a huge year of predators, okay, which is going to crash the rabbits, etc., etc. Some are not that predictable, okay, and we'll talk about those. All right, so where we left off, we were talking about the carrying capacity, or K. Remember, the carrying capacity is the number of organisms of a given species that can be supported by the habitat or by the region. And what determines the carrying capacity can be a whole slew of things. It could be food, it could be nesting habitat, it could be clean water, it could be interactions with disease, all kinds of things can drive the carrying capacity. And humans have a carrying capacity. We're not entirely sure what that carrying capacity will be, because with the invention of technology, we seem to be able to push the carrying capacity higher and higher. Right? So what we once thought the carrying capacity of the planet for humans was 2 billion. That's what we thought, in the early 1800s. We thought 2 billion would be the max. We were at 1 billion. We thought we could double the population, and that was about it. Okay? From a food resource point of view. But then came, the technology advances like tractors and seeds that are winterized or Roundup ready. Just the ability to grow a lot more food allowed us to have a lot more people. It wasn't a matter of space. We still have lots of places, lots of landscape on the planet that people don't live. It was a matter of food resources. Right? Now the thought process has kind of shifted, and most people are worried about clean water. That will be the limiting factor, is clean water. Now there's always a few people that believe it doesn't matter if you have enough food, enough water, and enough space, that when you get a high enough density of individuals, disease will knock the carrying capacity down. Okay? And that may be true. We've had some huge outbreaks before, like the Black Plague and the flu influenza in the 1800s, And that, I mean, that really killed off a lot of our population in certain regions. And it was because, well, most people think it was because our populations were really dense. Well, with modern medicine, are we going to be capable of preventing these large breakouts of diseases? Maybe. Okay. And so there are different predictors out there right now. The carrying capacity of humans on the planet. Some say it's around 9 billion. Remember, we're close. We're approaching 8 right now. So we're about a 7.7 or so billion people. Some think it's around 9 billion, and then other estimates have been more like 12 billion. Either way, though, probably in your lifetime, you're going to see that 9 billion mark, most likely. I mean, in 1940 or so, the population of the planet was 2 billion. So it's, you know, almost 2020. Okay, so in 80 years, we've added almost 6 billion people to the planet. And for most of you who are watching this, you know, you probably got a good 50 years left of your life, right? At least. So in 50 years, I highly expect us to reach, you know, add another billion and a half. So you'll be well over that 9 billion mark. Okay. We'll talk more about human populations later. They play a really important role in wildlife management, because one of the main stressors of wildlife management and fisheries management is the role that humans play. All right, the inflection point, we talked about this. The inflection point is half of K. Okay, so half of the carrying capacity. In this case, the inflection point is about 200,000, whatever species we're looking at, 200,000 individuals. That's also the maximum sustainable yield. So I went over this very quickly, and we're going to dive into this a little bit more. But if you sample a population of, say, fish or shrimp or clams or lobster or something at the maximum sustainable yield, and what I mean by sampling it there is you take only what is produced over the maximum sustainable yield each year. So basically, regulations allow you to take only the new reproduction out of that population. So you keep the population at the maximum sustainable yield or an inflection point. So it's not bouncing up next to carrying capacity. It's sitting at the level that is highest reproductive potential. And you're only taking the excess. So the population still stays at that highest reproductive potential. Then you're sampling your population at MSY, or the maximum sustainable yield. This, from a fisheries standpoint, is hugely important. Okay, and it probably, well, no probably about it. It would work for terrestrial organisms also, but we typically don't do that with terrestrial organisms in most circumstances. Okay, mainly because if, let's say, we're talking about ducks and we're talking about how many ducks can be taken, we don't know what's going to happen as those ducks migrate out of that state. We don't know what's going to occur to them in their migration routes and things like that. So you have to take into account, like, well, what's their food resource on their wintering grounds? What's the nesting habitat on their, you know, spring grounds, etc., spring summer grounds? So it's a little bit more difficult. And I'm not saying fisheries is easy, because fisheries, you know, a lot of the maximum sustainable yield is, hey, we're doing this in the ocean. Okay? And all of the oceans, I mean, they're basically connected. And so the ability for fish to move out of a region is just as easy as it is for a bird to fly from one region to another. The difference is the management of the oceans is different. No one owns the ocean. Now, There are regulations 200 miles out from land that the individuals that own that land own kind of the rights to 200 miles out. We'll talk more about this. Okay. But then after that, no one owns the ocean. So the regulation is put forth to try to get everyone in fisheries to act in a manner of, hey, we don't need to, decimate the world's population of certain fishes. And we've done that. Okay. You're reading the book Cod, and you can read that we already made, the Atlantic cod basically go extinct. Okay? There's so few, genetically speaking, they're not, they're probably not even a species anymore. But that being said, the Atlantic cod is recovering. Okay? Hopefully, mutations will take place in the Atlantic cod, and we'll get some genetic diversity and bring the populations back to what they once were. You can't fish Atlantic cod anymore. But it's that maximum sustainable yield that a lot of fisheries is after. Okay, terrestrial harvest can also do the maximum sustainable yield, but often they're not interested in that because they're interested in selecting maybe a single sex. So you're only going to hunt for males, or you're only going to shoot one male duck or one female duck and the rest have to be males, or something along those lines. When it comes to maximum sustainable yield, and the why it works better for fisheries is you're not sex selecting. Okay, so you're just taking whatever it is. Now you might have a size class, but it depends on the species. Okay, we'll come back and check that out. And we'll look at some examples much more detailed because you have an assignment that you're going to need to be able to calculate the maximum sustainable yield. All right, so if we go back to the growth curves, and so if you remember, we were talking about exponential growth curves, and we just said exponential growth curves is the change in n divided by change in t is equal to r, the intrinsic rate, okay, so the rate of growth, times n, the population. There is none of this, okay? So exponential is just that first piece of the equation. Okay? Logistic growth, you have to take into account that there's such thing as a carrying capacity. So when you're calculating your growth rate, you also have to know, okay, well, what's the top end? So K is carrying capacity, or the maximum number of individuals that the environment can sustain, and N is your population. As K gets close to N, or N gets close to K, you would realize that the top number here gets smaller and smaller, and when you divide something, a small number by a larger number, okay, you get really close to 0. If these two are identical to each other, K and N, so the population has met its carrying capacity, it will be 0. Okay? And then you have no growth rate because population can't grow anymore because it's met the maximum number of individuals the environment can sustain. Now that's kind of hypothetical because it's not like the fish are running this equation and they're saying, we're close to K. Okay, we made K, now no one can reproduce. That's not how it works. But from a management point of view, if your population's close to K, you know that any reproduction over K could result in a dip in the population or a large die-off in the population. So here's an example of that. So let's say the rate is 0.25. Let's say the K is 1,000. N is 990. Okay? This is what you would expect to add to the population is 2.5 individuals. Okay, so as you get really small, or as the numerator gets very small, this rate of increase is likely to change to be a smaller number. You can only add so many individuals. Now, in some cases, you have a huge influx, and you just get a huge die off. Okay. But we're talking about how many individuals is the population going to increase by. We're not talking about what's the reproductive output, because the reproductive output could be extremely large, but because the environment can't sustain any of those individuals that are being reproduced, you just have a bunch of dead fish or a bunch of dead birds or a bunch of dead mammals. So that's kind of how that plays out. Is we need to know the K, and sometimes this is very difficult to calculate K or find out what K is. A lot of that goes into, well, first of all, what affects K for this species? If it's a terrestrial mammal, okay, we might say, okay, what's affecting K? How many predators are in the region? If it's not a predator itself, okay, how many predators are in the region? Okay? How many? What portion of the population are they going to consume in a given year? What's the habitat like? How much vegetation is there? Is there enough vegetation to feed the entire population that currently exists? And then how many extra individuals can be fed? What's the disease outbreak like? Parasite outbreak? If they need, you know, if they need a certain habitat to escape harsh climates, like tall pines or something like that, what's that like? Is there enough that they can get out of, heavy winters, etc.? And it's, it's, I don't want to say it's a guessing game, but it's best case scenario. This is what it's going to give you. Okay? And that's where the carrying capacity is. Best case scenario. Then you have to look and say, well, okay, we're going to have a harsh winter though, lots of snowpack, etc. That's going to affect the ability of this organism to escape predators. Okay? We have more predators coming into the region, right? Or more disease coming in, or more parasites coming in. Okay, so carrying capacity can be difficult to calculate, but remember that it can change over time and it's not set in stone. And it's very important to calculate this because then we can manage populations to the best of their ability from a management point of view, whether it be fish or wildlife. All right, so back to these logistic growth curves. And the logistic growth curve is really broken up into three phases. Okay? The initial phase. So let's say you just introduced a population and you introduced like 2 individuals into the population or a handful of individuals in the population. Well, for that matter, we could probably just say, okay, this is like talking about when we reintroduced wolves to Yellowstone. Okay, I think we introduced like 20, 25 wolves into Yellowstone, somewhere around there. Okay, and so you had a base number. It took quite a few years. Okay? If this is years, it depends on the organism. This could be months, this could be years, this could be tens of years. Okay? It takes quite a few years to start hitting what we call the exponential phase. So those years, those early years are called the lag phase. And this is where organisms are trying to adapt to the new conditions. They're trying to adapt to the new environment. Okay? Maybe they're getting picked off by predators. Maybe they're entering regions where there's no food resources, and so they're wasting a lot of energy. These things. So that's a lag phase, and it could be much longer than 5 years or 5 whatever this happens to be. Eventually, though, if the conditions are correct and the K is high, you're going to get an exponential phase. You're going to get this phase where you have an extreme growth, an explosion of species or individuals within that species. Okay? And that can happen in a couple of years. It could happen over, a 5-10 year period or whatever it might be. Again, time is just dependent on what organism we're talking about. If we're talking about something that only reproduces every 3 years, then this might be tens of years. Or Each one of these digits might be representing every 5 years or every 3 years. If we're talking about organisms that can reproduce every 3 months, this might be representing 3 month periods or half a year. Okay, so really the time period is dependent on the organism that we're talking about. But that exponential phase can go for a long ways. Now, that exponential phase will top out eventually. And as it's topping out, what's happening is the population, the N, is getting close to the K. So that's why it starts slowing down. That's why the growth starts slowing down. And then you get into what we call a stationary phase. Now, the stationary phase is, like I said before, it's not this straight linear line, but it bounces up and down, kind of around K. Okay, so they might overshoot K and then crash a little bit and stay below K for a while, then overshoot it again, etc. But that phase is called the stationary phase, where your population growth is very slow, okay, and might even be stagnant to have no growth at all because you've reached your carrying capacity and you've reached your maximum. Okay, a couple things that will determine the population dynamics. Okay, we have two main types of factors that would determine the survivorship or the ability for a population to grow. Some of those factors are called density-dependent factors. Density-dependent factors are things that change, okay, or become more important as the density of the population, how many individuals you have in a given space, increases or decreases. Okay, so, for example, let's talk about like food supply. Obviously, if you have organisms that occupy a space on the landscape, as the density of those organisms occupying that space increases, the amount of food competition also increases. Okay, remember Robert MacArthur was talking about optimal feeding, okay, and I talked about him as being one of these individuals that, managers stand on the shoulders of these individuals that laid the groundwork. Okay, his optimal feeding and work with density dependent factors was hugely important for the way we manage species today. We realize that people who like to hunt and fish, they like lots of organisms in a small region, so they don't have to travel very far to see, a big bull elk or, a big, buck or to catch a bunch of fish. They don't have to travel very far to do that. But again, as you increase the density in a given region, you increase competition. As competition increases, survivorship decreases. And so it can just be lots of things can play that effect. It's not just food and water. I mean, it could be nesting habitat, space, lots of things. It could be disease and parasites. It could be predators. But all those factors are density dependent. Okay? As you increase density in a given region, okay, you can change the effect that disease has on a population or the effect that competition for space, nesting, behavior, etc. has on individuals, which can decrease their survivorship. Okay? You go the opposite way. You increase the amount of land or the amount of habitat so the density decreases in a given region. Okay? You can increase your survivorship because now you have more food supply, less predation, less parasite or disease effects. You might have more room for nesting or sexual reproduction behaviors and things like that. Okay? Now there are a set of factors that we don't have any control over, okay, and that has nothing to do with the density of the population. Okay? For the most part, it has nothing to do with the density of a population. Okay, and those are what we call density independent factors. Density independent factors, like the name suggests, are not dependent on how many organisms are in a given region. Okay? So just because you might have, you know, reached your K on one mountainside, and the other mountainside is, you know, half of K. It's at its maximum sustainable yield point or inflection point. That has nothing to do with how much snow this mountain peak gets versus this other mountain peak. So, or how much rain or how much wind or whether a tornado comes in, whether a hurricane hits it, whether an earthquake happens. Okay, these are all density independent factors. Now, I have to kind of make a little bit of a caveat with that though. Weather is density independent. However, severity of weather or frequency of weather events can be altered. At least the data suggests that it can be altered by density dependent or density of an organism, mainly humans. Okay, and okay, so what I'm talking about is, let's say we go out and we build a giant city in the middle of a desert, and we lay down blacktop, a bunch of buildings, etc., and the heat has nowhere to escape. Okay, and so if you want to see like thermal maps, you can, if you look at a thermal map of the United States, you can pick out exactly where all our major cities are at because of the thermal footprint that they put on the landscape. Okay, they change the temperature in that region. Okay? Well, changes in temperature in a given region can cause severe weather events. It can cause more tornadoes to occur. It can cause lightning storms. It can cause severity of hurricanes. Lots of things can occur when you change the temperature profile in a given region. So again, density independent factors are weather. Okay. However, the severity of the weather could be dependent on the density of a given organism, mainly just humans, though, because there are no other organisms that change the temperature of the landscape to the degree that we do. Now, there are some, okay? You know, you can say, well, beavers change the temperature of a landscape by cutting down trees. You might say, like, ants or things like that can change the temperature of a landscape by building large mounds and eating the vegetation away, or termites by building really large mounds and things like that. They could cast shadows on habitat and change the temperature in that region, but not to the degree that we can, and not going to change the weather patterns like we do. Okay. All right. So let's look at a kind of a practical application of that logistic equation. Okay. So again, remember back, the logistic equation is taking into account K, what's the carrying capacity, what's the rate of growth, and what is N, or what's the current population at. So again, change in N over change in T is equal to R times N. In this case, we're saying N is half of K, or N is at the maximum sustainable yield, okay, of this population. K is 1,000. So if we take this equation and we calculate it, we could expect that 62.5 individuals is going to be reproduced in this population in the given time period, whatever T is. If that's a year, then it's 62.5 individuals in a year. Now, what that tells us is we can take 62.5 individuals out of the population and not change the population size. The population size should remain at 500. Okay? because 62.5 is what we'd expect to be just added individuals into the population. Now, obviously, you're not just taking the new individuals in the population. Most of the time, you're not doing that, but you're taking individuals out of the population, and you could take 62.5, and it wouldn't change the population size. Now, again, you have to be careful with this, because what if out of the 500, only 100 are reproductively active? So 400 can't reproduce, and you take 62.5 and you sample, say 30 of the 100 are these reproductive individuals. Now you've changed the equation. You've changed your rate of growth, because now you don't have enough individuals to reproduce to get that rate of growth. Okay? So again, I want you to think about what these numbers mean. Rate of growth is calculated by how many births, how many deaths, so birth minus death, okay? And then immigration minus emigration. How many are coming into the population? How many are leaving the population? That's really how you get R. If you change how many births, R changes. If you change how many deaths, okay, so you take more than 62.5, okay, the number of deaths increase and the rate can change. If you have a bunch of individuals leaving the population because the habitat's not very good, not only is K probably wrong, K is going to decrease, but your R might decrease because you don't have enough individuals to add back to the population. So again, the inflection point is the point at which the population's growth is at its largest. Okay? That's the point why fisheries want to sample at that. And I have to correct something. Most fisheries units don't actually sample at the MSY. They don't actually sample at the maximum sustainable yield. They could sample at it, but they don't. They actually sample lower than it. So let's say this is a small fisheries or something like that, and your maximum sustainable yield would be a 62.5 take. Okay? Most fisheries units would say, okay, well, we have to sample under the maximum sustainable yield to account for some of the changes that could occur naturally in the population. You could have a reduction in food. You could have a reduction in habitat. You could have an increase in predation or disease or something like that. So maybe they would sample it at 55 individuals. So they give themselves a little bit of cushion, okay, and ensure that the next year that maximum sustainable yield is still at that 62.5. You haven't taken too many to decrease your population. Okay? All right. So you're going to go through some exercises for the next assignment, kind of calculating this and thinking about maximum sustainable yield along these lines. All right, so the Isles Royale, I just wanted to reiterate some of these pieces. I went over it fairly quick last time. This is the Isles Royale. It's a little island, okay, that's kind of shared by, well, Canada doesn't really own the island, but sometimes they manage pieces of it. Okay, but Minnesota, Michigan, Wisconsin, they all have researchers that research this island. And I want to say, I could be wrong, so don't quote me on it. I want to say that it belongs to Minnesota, okay, but it could belong to Michigan. Okay? But at any rate, it doesn't matter. It's part of the United States. It's this little island that's out here. And we believe that moose and wolves entered through Canada, crossed the water, and got onto the island, basically by swimming out to the island. Okay? So there's been teams of researchers from universities, University of Duluth, University of Michigan, that go to this island, and they've been tracking what's going on with the predator-prey cycle on this island. Right? And they've been collecting like moose skeletons, and you can see there's a bunch here because there was huge population of moose on the island, and then the predators came in. And so you might say, well, the moose really have nowhere to escape. They can't get off the island. Of course, the wolves are ferocious predators. They're going to just consume all the moose and they're going to go away. Well, that might have occurred. It's possible it could have occurred. Okay, but what we see is originally when the moose got on there and the wolves got on there around the same time, what you saw is the moose population increasing while the wolf population was increasing. So it's not a complete cycle. Right? It's not, the cycle wasn't set yet. Then you do start to see a cycle. So you see a dip in the moose population around the 80s, and you see a big increase in the wolf population. Okay? And then that dip might associated with this giant dip that you see in the wolves. So they could have out ate themselves. Right? They could have ate too many of the moose, and the moose population was low, so the wolf population kind of crashed. But then after you see that, you see this giant peak in the moose population, but the wolves are really low still. Right? And the wolves they never really rebound. I mean, we're talking about a huge difference in numbers here. And the wolf population is about 30 individuals on the island. Okay? And so they never really rebound. They bounce back and forth between 30 and kind of 15 individuals a bunch of times. And the moose population, okay, it crashed anyways. Okay? And then rebounded and then crashed and rebounded a little bit. So this is not a predator prey cycle that we see when we look at like lynx and hares. Okay? So they're not mirroring each other. It's not a direct relationship between the predator and the prey. The wolves are not driving the moose population down, and then that in turn is not causing the wolves to die out. There's something else going on, a lot of something else going on. Okay? And so what we learned from Isle Royale and studying this system is that predator prey systems are not neatly controlled. Okay? It's not a give and take predator prey model like we see in the lynx and hare. Okay? The lynx and hare situation is a really unique situation. They mirror each other very well. But in other predator prey models, this is not the case. And it really allowed managers to sit back and say, okay, the predators are not driving the prey population, but they can have an effect on the prey populations, but it's not that simple. There are other variables that play a huge role in what happens to populations, and you have to calculate and take into account those other variables. You have to talk about disease. The fact that the Isle Royale, that the wolves got a disease called parvus or the parvovirus, okay, and your dog can get this virus, and it's awful, and it'll pretty much kill your dog. But this happened to come onto the island and start knocking the wolf population really down. There's other things, okay, with the wolf population so far down, okay, the genetic variation that we see in the wolves is very low. Weather, okay, they had some extreme events on the islands, okay, on the island, okay. Food supply, we talked about this before. When the moose population got to its peak, we're talking 2,500 individuals or so, they pretty much decimated the vegetation, especially the low new growth vegetation. They ate themselves out of food. Okay? There wasn't enough habitat. And then just random events. You don't know when you might have a freak snowstorm, or you might have a freak weather event that occurs at, calving time or something like that. So there's a lot of features that go into the Isles Royale, but there's also a lot of things that go into all management of all big game or even fishery scientists. It's not this predator prey model where it's like, oh, well, we can pick, you know, this piece right here. If we remove all the predators from this region, we'll have plenty of deer. They'll all be giant deer. They'll all be, great, or plenty of elk or plenty of moose. No, it's not the case. I mean, we already know that from our Yellowstone work. When we removed wolves from Yellowstone, absolutely, it caused the population of elk to increase substantially. But then the elk ate themselves out of food, okay, and their population crashed again. And they weren't nearly as healthy as when wolves were in that ecosystem. Now, with the introduction of wolves back into the ecosystem, the elk are much more healthy, the populations are much more stable, and a lot of the weak individuals, a lot of the genetic variation that you don't want, the diseases that you don't want in a population, they're gone because the wolves are eating the weakest and the slowest individuals. And so you have to manage things not from a single individual's point of view or a single species, okay, but more holistic. Okay? And a lot of managers try to do this. Now, we'll talk about the pressures there are on managers and the reason why it's hard for them to do um, management from a holistic point of view. Okay, so what this Isles Royale really does is it kind of gives us what often is called this classical paradox in science, that the longer you study a system, okay, the less you can be certain about. Okay? And so the longer we know, or more data that we collect, the less certainty you'll have about that system. Because you start finding that ecosystems are alive, ecosystems are connected, and you get these ripple effects. You make one, decision on the ecosystem to either add new individuals, remove certain individuals, and you get this ripple effect. And often that ripple, it's just like a pool of water. If you see that ripple, you see the initial ripples, that's easy, but you can't see the ripples that are further out. Okay, that water's still moving. It's still having an effect. And you might not know until much later, until those ripples keep building up and building up, that you've actually caused something to occur that you would never have known about. Now, with that being said, of course, more knowledge, more studying of an ecosystem, studying of a situation will always allow us to better predict an outcome. Right? But the prediction really has to be, you have to be able to kind of alter it. You have to be able to go back on that prediction or go back on that management means of management. Okay. And what I mean by that is, let's say a manager says, hey, we're going to take 1,000 deer from this region, okay, because we've calculated this model and we think that 1,000 is not even, it's not even going to make a dent in this population. You take 1,000 deer out, and then your winter's harsh, so another 1,000 die, and now your population is actually low. Well, okay, I don't want to say it's a mistake, but you can't predict everything. You don't know what the winter's going to be like. You don't know how many are going to get hit by a car. You don't know how many predators are going to move into the region and consume your resource that you're trying to manage. Right? And Linus Pauling, for those of you who don't know Linus Pauling, he's an individual. He wasn't a wildlife biologist, and he was really not any individual that you would be like, why are we talking about Linus Pauling? But I'll give you a little information about him real quick. Like, Linus Pauling was a kind of a high school dropout. Not even kind of. He was a high school dropout. So when he was like 16 years old, he decided to drop out of high school in Oregon. Okay, so he's going to high school in Oregon, and he felt that the high school was just too easy. It wasn't challenging him enough. And he didn't like it, so he decided to drop out and go to college. Okay? So he dropped out of high school, went to college, okay? Got his degree at Oregon State, and then got his PhD. Okay, and he's a biochemist, and he got his PhD, and then he won a Nobel Prize. Okay? He won another Nobel Prize. He's the only man to win two Nobel Prizes and solo. Okay, he won them by himself. Okay, so he's really famous, and he won the Nobel Prize for his work that was done with describing protein shape. Okay, so he described the shape of alpha helix proteins and beta sheets and things like that. He also tried to describe the shape of DNA, but he was wrong. But nonetheless, Linus Pauling, very, very famous biochemist from the United States. And he had this quote that he used to say, he says, I don't care to comment on the future of anything. And he often would say this about war or peace or things like that. But he even said this from a scientific point of view, that a job like being a manager and having to model and predict the future of a population is very, very difficult. Even for individuals who are considered geniuses, like Linus Pauling, he would say, I don't care to do it, and I'm not going to comment on the future of anything because it's not predictable. It's tough. All right. So with that, make sure you check out that assignment. And if you have questions, again, you can always contact me. And we'll talk about probably methods for capture and maybe methods of monitoring populations and things like that. We'll stick with populations for now, and then we'll move on to something else in a little bit.